so you may hop on. Okay, good afternoon, students. So just some quick announcements about Carmen. So if you logged in and saw they had a bad grade, I apologize. We were working on readjusting some of the weighting and the scores based on us removing some of the final project work for you all. So we need to adjust accordingly. So it should all be back in order now. So what we'll do in previously, when you were supposed to have presentation grade, final project grade, those have been absorbed into the final team assignments, and then individual assignments are weighted, and then as well as like other group assignments from the beginning, most of the drafts and the smaller assignments should all now be organized in Carmen. And then the remaining percentage we've absorbed into a kind of participation, class engagement, group engagement grade that will be partly determined through the faculty evaluation, but then also through your team final survey. So if you have any questions, please let us know. But for the most part, the aim was to try to reduce the overall workload. So if anything, has greatly benefited you all. So let me know if you have any questions or concerns, but yeah, over to you.
Great, thank you, Patrick. So this is, at last, you've all been waiting for this. This is the last talk on filtration. We're going to introduce enclosed stacked rapid sand filters briefly, talk about some of the advantages and challenges of working with stars as a filtration method. So I want to begin with this insight about what is different between when you finish backwash of a stars filter compared with a standard rapid sand filter. With a standard rapid sand filter, when you backwash, you are always pushing water up through the sand. And so there is water above the sand that just was used to backwash the filter. And so if you haven't run water for a very long time during backwash, there is still a higher concentration of turbidity or particles in the water above the filter when you finish backwash. And then when you start filtering with a conventional rapid sand filter, you start putting water in the top of the filter, and that water goes down through the sand. And so that means that the first water through the sand in a conventional rapid sand filter is the water that was just used to backwash the filter, which is slightly dirty. And that is one of the reasons why the first water that comes out of a rapid sand filter is a poorer quality, in addition to the fact that the filter is still in the ripening stage. Okay, so let's look at what happens in a stars filter. In a stars filter, here's the stars filter like in backwash mode. And when we open up this valve up here and stop the backwash exiting through that siphon tube, then water continues coming in through this inlet box. And the question is, where does that water go? Well, the water that's coming in the inlet box wants to, or the only option for it to leave is to get to this outlet box, because the outlet through the backwash siphon has been blocked. So the only outlet is through the outlet box, but that outlet box is quite high. And so the only way the water can get into that outlet box is, first, it has to increase the water level above the filter. And so once you get to filtration mode, it looks like this. The water level has come up in the filter box. And so the water that is now above the filter in that filter box is a mixture of water that was there right at the end of backwash and water that got injected somehow as that box was filling. So the question is, where does the water come from that fills the filter box at the end of backwash? So how does the water get into the filter box? How does the water get from this inlet box over to the filter box? And the answer is, it goes through these 4 inlet pipes. Some of it goes in at the top, some of it goes in lower, some of it goes lower, some of it goes all the way at the bottom. But if you're water and you're lazy and you try to find the easiest path, where do you most likely enter? The shortest path is to avoid the sand. So the easy path is to go in this very top inlet, go into the very top of the sand bed, and then go up into the filter box. That makes sense? So that's how the water gets into the inlet, into the filter box at the end of backwash. So does that water is slightly dirtier because it includes water that went through the filter during backwash. So does that water ever go through the filter? It's interesting. And Ravi's got it. The answer is no, it never goes through the filter, because the next thing that's going to happen is you're going to switch over to backwash mode. And when you switch over to backwash mode, you flush all of that water through this siphon pipe, and it goes to waste or to your backwash recycle tank. So the water that's above the filter in a STARS filter never gets filtered. It gets dumped. So it's both a good thing and a bad thing. It's good that, because that's dirtier water, it's good that we're not filtering that because it's dirtier water. It's bad in that we end up dumping a fair amount of water to make this transition between filtration mode and backwash mode. One more advantage, there is no danger of running out of water, out of filtered water to backwash the filter. So in a conventional system, you backwash the filter with a rapid sand filter, you backwash with water that you filtered and you put in a clear well tank. And then you take that water from that tank and you pump it back up through the filter. And if that clear well tank is empty, you're stuck. You cannot backwash your filter because you don't have water to do it with. And that is actually a failure mode for a conventional water treatment plant. This can't happen with a STARS filter because we don't use filtered water, we use clarified water. So that means that as long as there is water coming into the plant and going through your flocculator and your clarifier, you've got a source of water to backwash. Of course, with the caveat that there must be enough water coming in to fluidize at least one filter sand bed. And now I want to talk about enclosed rapid sand filters, enclosed stacked rapid sand filters, and open stacked rapid sand filters. So enclosed versus open. There's 3 enclosed stacked rapid sand filters that were built for a village in India, in Jharkhand, India. And there's the big box, a big filter box for a open stacked rapid sand filter. In your assignment that you're working on, I forget what the minimum flow rate is that you came up with for your filter, but it's somewhere on the order of 10 liters per second. That if you're trying to design a filter that's less than 10 liters per second, it ends up being too small for a human to comfortably work inside and build this tank. So that sets a minimum flow rate that we can use for open stacked rapid sand filters. And then below that, we have to switch to enclosed built inside a pipe systems. And they have their own advantages. They don't require as much excavation. They don't need to be so tall. An open stacked rapid sand filter ends up being close to 5 meters tall by the time it's all, or 5 meters deep. It's this really deep tank. The enclosed filter doesn't have to be so deep. So here's, let's see if we can figure out why. So here's 3 views of the filter, both looking at it from 2 different angles and also a section cut. So there's a tall inlet tank There's a shorter outlet tank. There's this lovely filter canister, which I think in this case is probably like a 2-foot diameter pipe. There's no longer an air release valve that is used to trigger backwash. Here we just use a standard valve, and that's partly because these are now much smaller valves and they're not so expensive, and so it's not worth going to the air lock system. They have the same system of 4 inlets and 3 outlets, which you can see in this middle view, and you can see water going into the filter and out of the filter, and it was a bit of a challenge to figure out how to get all those pipes to line up. Working in the round is more complicated than working in rectangles to figure out how to get everything lined up. But that's at least version 1 of our design. Of course, there's sand inside this filter, and notice that the sand bed is a much bigger fraction of the total height of this filter, because there's something very different about it. So what happens in backwash? So let's think about what's happening over here in this filter, and let's assume that this valve is open and backwash is happening, which means that water is coming from this inlet tank. All of it is going down through this bottom pipe, going up through the filter and out. So what happens if we close that valve? Can anybody see what's going to happen? If I close this valve, and this pipe might be 3 inches in diameter. And so if I close this valve, what happens to the water in this pipe? Maybe it's just so obvious. That water runs out and the pipe fills with air up to the valve. So then what happens when we try to start the next backwash? So the next time you want to start backwash, we open up this valve and now it's atmospheric pressure way up here at the valve, and the height of water in the inlet tank is right here, which means that there's hardly any difference in potential energy available to push the water through the sand bed and fluidize it. So here's the insight. We were counting on atmospheric pressure being way down here so that there's enough of an elevation difference or potential energy difference between the inlet tank up here and where the backwash outlet is down here. So there's enough head or potential energy or elevation difference available to fluidize the sand bed. So if this air fills this pipe, we can't backwash. It fails. We cannot get backwash to start. So there's 2 potential solutions. You could try moving this valve to the very end of the pipe, but it's still vulnerable because when that valve is open, it's still possible for air to sneak up the pipe past that valve and empty the pipe of water. So the elegant solution is to add a water seal at the end of the pipe that prevents air from ever getting into the pipe. So here it is. It's a very simple thing. It's just, I'm proposing maybe a 6-inch PVC cap with a little pipe stub in it. Or it could be a bucket, a small bucket. And the water from backwash enters that bucket and then it overflows the bucket. But the bucket always remains full of water. And that means that when you close the valve, there's no way for air to get up into that backwash pipe. And that means that the pressure at the end of this pipe, it's atmospheric right at the overflow of that bucket of the water seal. And that means that we have the pressure difference that we need, or the head that we need, between the inlet tank and the backwash outlet. There's enough energy there to drive fluidizing the bed. So that water seal ends up being a critical piece of the design. If you don't have it, the system fails. Anybody want to ask a question about that water seal? We're making sure that there is no way that that siphon pipe can fill up with air, so that there's always this hanging column of water there, because we need that dense water to lower the pressure inside the top of the filter. Okay, so let's look at the pressure inside the top of the filter. Here we go. So this is a view at the end of filtration. At the end of filtration, the water level in the inlet tank might be way up here. Okay, and that water is coming from the inlet tank. It's going down through all of the pipes and into the filter. And let's follow this bottom one. So way down here, let's put a manometer in and see how far the water rises. So we look, and the water rises in that manometer almost up to the same level as where the water would be in the inlet tank. The only difference being maybe there's a tiny bit of head loss in this inlet pipe. And so that would result in there being a slightly lower pressure at the bottom of the filter than if there weren't any head loss. And at the top of the filter, same thing. It should have been exactly the same water level. Manometer gives the same reading at the bottom and at the top of the filter. Okay, the pressure at the bottom of the filter and at the top of the filter, as measured by a manometer, are the same. And of course, there's sand in that filter. Now, what happens if I drill a hole in the top of the filter during filtration? So let's do that. Let's drill a hole. So I just put a hole in the top of the filter. Maybe the hole wasn't very clear, but there it is. There's a hole in the top of the filter. And I want to know, is air going to come out of the filter? Or sorry, is water going to come out, or is air going to go in? And if everybody who can could just go video, and we can just do a quick show of hands. Who thinks water is going to come out of the top of the filter if I drill a hole there while we're in filtration mode? So hands up, or raise your hand if you think water is going to come out. And I know I've what's it called? I've discouraged all of my students because you've learned that I ask these questions and then they're tricky, and then you're just demoralized because you're wrong again. Oh man.
Do we want to pull a choice 1 or choice 2 poll?
Okay, sure. So, and it can be water comes out or air goes in. You got it. Choice 1, choice 2. Okay. Go ahead and vote. Which way do you think it's going to go?
Choice 1 is air out.
Choice 1 is water out, and choice 2 is air in.
Okay, so what's the actual schedule for what we on?
Okay. What do you think, guys? I'm eager to see. So water comes out 60% and air goes in 40%. And this time, science by consensus works. The 60% of you who said water comes out are exactly right. And the way you can know that is because these two lines that look, this top manometer is essentially connected to this fluid that's in the top of the filter. And the pressure there is represented by the water height in this manometer. And that water height is well above the top of the filter. And that means water will come out. Or put another way, if I had installed a manometer in the very top of the filter, it would have also come up to this top blue line. So water would leak out, okay? Now let's do the second case. Hang on a second, I want to make sure I know where I'm at. Okay, what about this one? What happens if I drill a hole in the top of the filter during backwash? So during backwash, this valve is open, the water is gushing out of this pipe and spilling, I guess, onto the floor and onto my computer at this water seal. And look at this. Look at what this manometer is telling us. It's saying that the water pressure right at the sand level is actually way down here. Is that a surprise? Why is the water level so low? Where would the water level be if I plugged a manometer, into, well, look, the water is exiting into this little bucket at the bottom here.
Yeah, let me look around.
That free surface represents atmospheric pressure. And as we go up, the pressure has to drop, right? As you're going up in a swimming pool, the pressure drops. So as we go up, the pressure has to drop. And that means that the pressure inside the top of the filter is way below atmospheric pressure. Okay, cool insight about E-stars. So now let's drill a hole in the top of that filter. Can we just resurrect the previous poll and have you vote on that one? Does water go out or does air go in? Does anybody want to just respond? What do you think is going to happen?
Doesn't air have to go in to equalize the pressure?
That's right. And it's because the pressure inside is actually way below atmospheric pressure, and the air is going to want to go, or the fluid is going to want to go from high pressure to low pressure. It's high pressure outside, it's low pressure inside, and so air goes in. So we're not going to actually drill any holes in the top of the filter, but I just wanted to make it clear that we're doing a very different thing when we switch between filtration mode and backwash mode in an enclosed stack rapid sand filter. In an open stack rapid sand filter, we manipulate the pressures by dropping the water level a really long distance in the filter box between filtration mode and backwash mode. The water level drops more than a meter in order to get the pressure lower at the top of the filter so that there's enough energy to actually back fluidize the sand. In an enclosed stacked rapid sand filter, we also change the pressure, but because it's enclosed, it's much easier. When it's operating in filtration mode, it's connected to an outlet tank that's at this kind of level. And when it's in backwash mode, its outlet is way down here. And so simply by opening up this backwash valve, we switch it so that it can access that new low water level, and the pressure like instantaneously drops. And we don't have to dump any extra water. We don't have that big chunk of water above the sand that we just waste. Anybody want to ask a question about that? here's a view of what all's going on inside the filter. So remember, we have a tall inlet box because that's where you get more and more head loss, more and more water level rise as the filter clogs. So that's happening inside here. That's where the clarified water is coming in through a hole in the bottom and then exiting through a bunch of pipes. So let's get rid of the outside of the tank. Okay, so I'm just deleting the outside tank so we can see what's happening inside it. So we can see all these, all the flow of water down into the 4 inlets, 1, 2, 3, 4, water coming in through this crazy system that includes water coming out of this pipe. So this is the water coming from the clarifier, comes up through this pipe, flows over the top of this, what I call a weir. It's the edge of the pipe. It flows over that edge of the pipe. And if you have multiple of these filters working in parallel, it's important to make sure that each of their weirs is at the same elevation, because that's what distributes the flow evenly between the filters. If the flow rate through your plant is low, remember we had a trick with the O-stars, the open stacked rapid sand filter, that we could open up a weir and get more flow to a filter so we could backwash it. Same thing is true here. Here we would just remove this, it's either a pipe stub or I believe it's a pipe stub. Remove this little pipe stub, and that will lower the elevation of that weir, and that will cause water that was going to the other filter to come to this filter instead. I'm playing with the idea of using a linear flow orifice meter here so that you can actually see what the flow rate is through the filter. The water is going through this linear flow orifice meter in reverse, in that it's going from the inside to the outside, whereas what you saw in the entrance tank, water was going from the outside, the entrance tank, into the LFOM and down into the flocculator. So here it's just backwards, but the same physics applies. And then water comes back up out of 3 of these 3 pipes. And if you are filtering to waste, it goes down this line, which would be a waste line. And if you're not filtering to waste, you would plug a little pipe stub in there, and then the water would be forced down this pipe, and that would be your filtered water pipe. So those are the controls. They're like doing very, very similar things to what's happening in the O-stars. The advantages, it can be built in a factory. It's easy to add an extra filter to expand capacity. You don't waste as much water as you transition between filtration mode and backwash. There's no big flush of a lot of water above the filter. And this is one of the things that this is one of our projects at Our Cloud of Reach. We're still working on creating the design for this and developing the fabrication method so that this is relatively easy to assemble. So that's an ongoing project. A few more things about other challenges with stacked rapid sand filters. We started using slotted pipes, both for the inlets and the outlets. And if you think about this, the inlets are getting clarified water and they're injecting that into the sand. Clarified water has some flocks in it, so it's not entirely surprising that there might be some particles in that clarified water that could clog a 0.2 millimeter slot. And indeed, that happens over time, that the inlet slots would slowly clog. And so that was a maintenance issue because you had to take the sand out of the filter in order to access those pipes and then clean them. And so in 2015, we replaced those inlet slotted pipes with this wing system, which I've shown there, which has this inlet pipe with what we call a wing below it, and then there's orifices drilled all along the length of that pipe that the water comes out of. there's been this dream for years that we could replace the outlet slotted pipes with something similar. We haven't figured out a reliable method to do that yet. It's still worth doing more research to see if we can figure that out. The failure mode is that if anything happens that too much water starts flowing into the outlet, it's easy for it to fluidize sand and then carry sand into the outlet. And you don't want that because you don't want to lose sand through your outlet pipes and send it to your distribution system. So that is such an easy failure mode. We haven't figured out any reliable way to prevent that from happening. And so we are still using slotted pipes on the outlet pipes. A challenge is that there's in O-stars, there's this big waste of water from that big flush that has to happen to get the big water level change. If we end up using our backwash recycle system, that ends up not being quite as big a disadvantage, but it certainly would be nice to not be wasting all of that water. And I want to also make this pitch that, yeah, we've been playing with these filters for over a decade, and there's still a ton to learn. You think about rapid sand filters dating from, I don't know, right around 1900. So over 100 years of people using rapid sand filters. We've only been using these for a decade. There's still a ton to learn. And there's so many places where we just somewhat arbitrarily, but with some good engineering judgment, picked some values, and then we've stuck with them ever since, knowing that those it's not possible that those are the actual optimal values. So we have never experimented with changes in the filtration velocity, with changes in the sand diameter, with changes of the layer depth. All those things we kind of went with a reasonable value at the beginning, and then we didn't touch it. Clearly, unless I'm just have an amazing ability to roll the dice and get the right answer on the first try, none of those can be optimal. So there's lots of room for opportunity, lots of opportunity for more breakthroughs. Yeah, more research needed, which is why filtration research is one of the things that is happening at Ohio State. Just as a diversion of a completely different system, here is a package filtration plant that you can take to a community, run the water through this filtration system, and provide clean water for the community. And I wanted you to just look at this system and see, like, from what you've learned in our class so far, what do you see? What's there? So I'd like you to ponder flocculator and clarifier and how many of you do see a flocculator in here?
Monroe, what's the alum mix tank? Would that be the flocculator?
Hannah, excellent question. So yeah, so alum is their coagulant. They have an alum tank up here. That's their stock tank, and they're using a venturi to get that into their raw water coming in. And yeah, water goes into this tank, and they call it an alum mix tank. It's like a little flocculator. The only energy source is actually the jet of water coming in, from this pipe. And that jet of water does provide some mixing and some fluid deformation. And so there is some flocculation. It's a terrible design for a flocculator, but it is a flocculator. What about a clarifier? Okay, there is none. No clarifier. So where are all the particles being removed? filter's doing all the work, right? Everything, the filter's doing all the work for removing particles. They have two filters in series. If I had my way, I would get rid of one of those filters and put a clarifier in its place, because a clarifier would reduce the particle concentration so much and help make that filter have a much easier task. And then just for fun, how many valves do you see? Right, this little symbol, the little cross is a valve. So this little thing right here, that's a valve. So roughly how many valves do you see? I don't know. It's something like yeah, go ahead.
If 15 or something like that.
Yeah, something like that. I didn't actually count precisely, but it's something like that. And how many valves are there in an agua clara plant between, if you're a water molecule going through the plant, how many valves do you go through on the way through the plant? I'm having to think about this too. It's like a trick question. All we know is it's not -1. Look, there's a valve. Presumably, we have to control how much water is coming into the plant. And so just before the water gets into the entrance tank, there's got to be a valve somewhere that the operator can play with to control how much water comes into the plant. Right, you know this? Like the amount of water that's coming into the plant, if it rains, the amount of water coming into the plant doesn't suddenly increase. It's controlled. There's a valve somewhere that's controlling how much water comes into the plant. So water goes through a valve there. It enters the entrance tank. It goes through the LFOM, into the flocculator, into the clarifier, into the inlet box for the filter, down into the filter, up out of the filter and into the outlet box, and onto the distribution system, and it's never gone through a single valve. Isn't that interesting? There are no valves in the path of water through an agua clara plant. There is an air valve that's opened up and closed when you want to do the backwash, but the water that's leaving the filter doesn't actually go through a valve, even in backwash mode. So that's just like, that was part of our philosophy. Get rid of all those valves, because every valve is a potential failure point, because you know this, everything that moves fails eventually. Every moving part is eventually a failure point. Okay, and then this was just a rhetorical question. What do you do if the filter is clogged and the backwash storage is empty? So see that tank up there at the right? That's where the clean water goes after you've filtered it, and you're storing some right there. You don't let people have, because if you need to backwash the filter, that's where you pull water from. And what if something goes bad? Like there's some extra dirty water coming into your plant and you don't get the alum dose set right. And so actually you get the coagulant dose set right, but there's no clarifier. And so all those particles end up in the filter. It clogs the filter really fast, and you haven't yet made enough clean water to fill up the backwash storage tank. What are you going to do? This is just this is a dilemma. So this is actually a failure mode for this system, that if the water coming in is too dirty, they won't be able to backwash often enough. They won't be able to produce enough water to fill up their storage tank before they need to backwash again. And the whole system grinds to a halt. And in that case, I'm actually not quite sure what I would do. Somehow, I think you have to compromise, and I think you have to do something nasty, like dump dirty water into your clean water storage tank so that you have enough water to backwash the filter. Katie didn't like that at all. Yeah. But you think about it, if you're stuck, you're in a village, you have no clean water, and you need to backwash your filter in order to make clean water, you've got limited options. Wasn't that fun? Okay. A few conclusions. Filters are really well suited for taking clean water and making it cleaner. They are not a good choice for treating slightly turbid surface waters greater than about 5 NTU. Meaning that if you look at the water and you see that it's dirty, it's too dirty to treat with a filter. They do remove particles and dissolved organic. Oh, sorry. The goal is to remove most of the particles and the dissolved organics using flocculation, flock filter, and plate settlers, and then you polish it off with the filter. Filter is the last thing you do after the water is already clean. A couple advantages of, that's pretty funny. I have written here 3, and it looks like that list is longer than 3. So it raises questions about my ability to count to larger numbers than 3. So 3 big advantages over rapid sand filters, and things come up in reverse order. Okay, so it's more compact, uses a smaller filter area. It's self-backwashing. You don't need to have any pumps. There's a single air valve that's used to control the whole system. So no big valves needed. It uses clarified water to backwash, and that clarified water isn't chlorinated, which means that the filters never see any chlorine, which means that the filters are biologically active. So this is biologically active filtration. We have not done any research on whether or not that's providing any added benefits for us, but biologically active filters do help reduce the dissolved organics a little bit further, and that's good. And we use hydraulic controls for the whole system to assure steady flow distribution between filters. And the more I learn about conventional water treatment plant design using mechanized system, the more I like this idea of just using simple hydraulic controls. Mechanized water treatment plants tend to have a lot of problems with getting their computer controlled system to provide steady flow through their filters. They're using computer controlled valves, maybe at the effluent side of each filter, to control the flow rate of water through each filter. And those mechanized valves easily oscillate. And so you don't get a nice uniform flow through the filter. And as you can imagine, if you have changes in flow rate through the filter, you tend to see poorer performance when you increase the flow rate, because some of the particles that had nicely attached, now when you increase the flow rate, the shear level goes up, and some of those particles get sheared off, and you end up with more particles showing up in the effluent for a little while. So steady flow is important. I don't know if I made this point perfectly clear earlier or not. If you would take like the previous system that I showed from the life water system, and if you would turn off the coagulant to the system and you would run dirty water through a filter, you would find out that the removal efficiency is really, really lousy. Like maybe you remove 50% and maybe you only remove 10% of the dirt if you don't have a coagulant. So the coagulant is absolutely critical in order to make this system work. So rapid sand filters and STARS filters require pre-treatment with coagulant. And I just keep on saying this because I feel like it's a mantra that is so important. sand filters cannot treat highly turbid water. It just doesn't work. Okay, I have a slide, and I'm hoping that you can just grab these presentation from the course website. So these are questions that I would love to have each of the teams in Gather discuss. And it's thinking about, how does this work if you've built a plant and now the community is growing and they realize they had 2 stacked rapid sand filters using E-stars, and they need a 3rd one, and they need to connect it up. And I want you to think about, well, what does the plumbing look like that would connect these filters together? And to be fair, I haven't showed you this, but I want you to think about, like, the water's got to get to all the filters. You got to, all the inlets and outlet stuff has to work. So how many plumbing connections does it take to add another filter if you want to expand the flow through a plant? And then how does an operator see that an E-stars is clogging? Like, where would you look to see that the filter is clogging? And how might you make it easier for the operator to know the filter flow rate without having to look inside the filter inlet tank at the LFOM? So the LFOM is hiding inside this tank. How could you make it easier for the operator to know what the flow rate is? With that, I'll let you go to Gather, and I'll see you there in a few minutes. See you.